All right, so we are in section 5.5. We skipped section 5.4. We are going to talk all about counting techniques. So the counting with multiplication rule, counting with permutations, and counting with combinations. We will then talk about non-distinct items, and then eventually lead to probabilities with combinations and permutations. So the multiplication counting rule, permutation, and combinations in and of themselves are not probabilities. They are ways in which we calculate the total, or in some cases, the denominator that we have when working with certain problems. All right, so first problem we're going to work with is what is called counting with multiplication rule. So here is an example. The fixed price dinner at Mabenka's restaurant provides the following choices. So you make an appetizer, which is either soup or salad, an entree of baked chicken, broiled beef, baby beef liver, or roast beef au jus, and the dessert of either ice cream or cheesecake. And you want to figure out how many different meals could be ordered from these selections. Ordering a meal requires 3 separate decisions. You must choose an appetizer from 2 options. You must choose an entree from 4 options, and you must choose a dessert from 2 options. On the next screen is going to be a visual tree diagram of all of the possible combinations. Your first choice is soup or salad. Then from there, you have 4 meal options and 2 dessert options. And then on the right-hand side here are all the possible combinations, for which if I total them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total options. Now, instead of doing a table or tree diagram like this, it makes a whole lot more sense to follow a formula. So we had 2 choices for soup, and of those, after that, we had 4 choices for an entree. So at this point, we are up to 8 possibilities. We then have 2 choices of dessert, so times that 8 by 2 gives me a total of my 16. So this is called, the way I like to think about it is a multiple choices question. Do I need to make a sequence of choices or a sequence of decisions? The way that we're going to figure this out, if there are P number of ways the first thing can be done, Q number of ways the second can be done, R for the third, fourth, fifth, whatever, however many we have, you're just going to multiply the number of ways each decision can be made to get your total. Here's a similar example. The International Air Transport Association assigns 3-letter codes to represent airport locations. For example, the code Fort Lauderdale International Airport is FLL. If you've been to Midway, there's MDW. O'Hare is ORD. How many different airport codes are possible? Well, we have 3-letter codes that need to be filled. So I need a letter in the first spot, a letter in the second spot, and a letter in the third spot. Well, how many letters are in the alphabet? 26. I have 26 choices for the first spot, 26 choices for the second spot, and 26 choices for the third spot, which if I multiply that all together, I believe it is all worked out here on the slide. I have 17,576 different airport codes I could create. Now, we don't have that many airports, but there are that many possibilities. 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, So we got chair. Second is vice chair. Third is secretary. How many different committees could be possible? Well, I have 14 people to pick for the chair. Once that first person is chosen to be chair, I cannot reuse that person. I'm now down to 13 that would be placed for a vice chair. And now 2 positions have been filled. I've got 12 members remaining to take the secretary position. We just have to be very careful here. This is called without repetition. We cannot reuse a person. A person cannot be reused here. Versus back here in the airport, letters could be repeated. FLL, a letter can be repeated. So there is a slight difference between the 2 of these. If they clearly say like with or without repetition, that's something that will help you figure that out as well. There are 2,184 different structures that could happen here. Another thing we're going to have to work with is what is called the factorial symbol. So the exclamation in English, the exclamation point, is called the factorial in mathematics. So the factorial is telling you to multiply all the numbers from what you have down to 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. When you are using the calculator that I show you does most, you can type in 5 factorial or 5 exclamation point, 10 exclamation point, and it will give you the answer. Just to show you. So 5, I can type exclamation, it gives me my answer. 10 exclamation point, it's going to do all the math for me. So it knows exclamation stands for factorial, and it will do the multiplication for you. This is used as we move forward into these permutations and combinations here in a little bit. You've just been hired as a book representative for Pearson Education. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? Well, let's call the schools A, B, C, D, E, F, and G. School A could be visited 1st, 2nd, 3rd, 4th, 5th, 6th, or 7th. So there's 7 choices for school A. There would then be 6 choices for B, because once A spot has been determined, that one value is gone. 7 for A, 6 for B, and then there would be 5 for C, so on and so forth, all the way down to 1. So if I wanted to, instead of typing in 7, 6, 5, 4, 3, 2, 1, I could just use 7 factorial, which gets me 5,040 different routes. We are next going to talk about what is called a permutation. A permutation is an ordered arrangement, that's key, in which R objects are chosen from N distinct or different objects so that R is greater than or equal to N, and repetition is not allowed. The symbol NPR represents the number of permutations of R objects selected from N total objects. So in order to do a permutation, we have to have all of the objects are different in order to follow the basic permutation formula here. All our objects are different. We cannot do any repeats. And order is important. I must place them in a specific order or arrangement. So those are key terms to look for as you're reading word problems to determine, hey, is this a permutation or eventually a combination? Here's the formula. NPR is calculated as N factorial over N minus R factorial. Now, I will show you how to do it by hand here in a simple example. And then from there, we will just use our technology. We want to evaluate 7p5 and 5p5. The way you would do this by hand, again, we're not going to do this by hand here, but I'm going to show you. The first number is what goes on top with your factorial symbol. Then subtract the 2, and that's what goes on the bottom with the factorial. So 7 factorial over 2 factorial. So 7 is 7, 6, 5, 4, 3, 2, 1. Or stop at 2 factorial because the 2 factorial drop off down here. And then I'm left with 7 times 6 times 5 times 4 times 3, or 25, 20. We are going to use Desmos to help us here. You have your option to go into functions. It's down here. So NPR 7, 5. So the way Desmos works is you have NPR, the function first, and then the larger, and then the smaller. You don't have to go to that function button. If you are on a computer, you can just do little n, capital P, lowercase r, and it automatically knows that that's what you want to do. So I think the next one it wanted us to do is 5, 5. And that's 120. So that is there for you. I will show you. I know some of you probably have TI-84 calculators, so I'll show you that in just a second. The 5p5 was 120. That's what I got there. Okay, if you are using a TI calculator, the way you are going to do this is you enter the first number, then you hit math, arrow over to PRB, arrow down to whichever function you want. So you're going to want to find the NPR button, click enter, and then hit the second number. 3. So 5, NPR2, you'll click enter, and it gives you your answer. Okay, so just know those are also other little things you can always search on Google really quick. If you don't remember how to find a certain function in your calculator, they're all there. In how many ways? So anytime you hear this in how many ways, that is your clear clue that we're not doing a probability. This is either a multiple choices, a permutation, or a combination question here. So in how many ways can horses in a 10-horse race finish first, second, and third? Trick here is I have to finish in a position, first, second, third. It matters where I finish. So a permutation is required. All 10 of my horses are in fact distinct. One crosses, and then the next one crosses, so on and so forth. So I have 10 total horses, of which I want to permute 3 of them. I want to arrange the first 3 places. So 10p3 is what I would do in Desmos. So lowercase n, capital PR, open parentheses, 10, 3. And the result is 720. And it does show the hand way here. Please use the technology. It's here to help you. I got the answers super fast. My goal is for you to get the answers correct and be able to understand them, not worry about, hey, can I use this formula? Okay, we already have enough math going on in the first sections. Just use the functions here. The next type of problem we're going to work with is what is called a combination. So here's the difference. A combination is a collection of objects without regard to order. So we're collecting, we're grouping, we are not ordering, arranging, anything like that. So the example I always like to take is if I have a class of students and I'm going to put you into groups. It does not matter whose name I say first. You're all in the group together. Doesn't matter if I say Joey, Kelly, and Kim are in a group. That's the same group as Kim, Kelly, and Joe. The order doesn't matter. I'm only grouping you together. So combinations are going to have less total possibilities here than a permutation would. Roger, Ken, Tom, and Jay are going to play golf. They will randomly select teams of 2 players. List all possible team combinations. That is, list all of the possibilities. And then we'll see if, hey, we get the same answer. If we pick pairs, Roger with Ken, Roger with Tom, Roger with Jay. Ken with Tom, Ken with Jay, and Tom with Jay. All pairs of 2 chosen from 4 people. Well, let's see. If I do the value of 4C2, guess what? I get 6. This is a way, again, to work with larger things, and rather than listing all of the possibilities, I can use a function to help get the answer. The number of different groupings of R objects chosen from N objects, in which, again, they are distinct or different objects. There is no repetition. However, in this case, order is not important. And here is the formula. So the other formula, the P formula, had the N factorial over N minus R factorial. For combination, we also put an R factorial in the denominator. Again, this is another reason why I don't like doing these by hand, because they get a little more messy. And there's no reason for you guys to do them by hand. So I'll show you how to do one, and then the rest of them we're going to do in the calculator. 4C1. If I were to do that using the formula, the total is 4. So 4 factorial would go on top. I would put 1 factorial, which is the value, and then their subtraction, 3 factorial. So 4 factorial is 4 times 3 times 2 times 1. And on bottom, I have 1 times 3 factorial, 3 times 2 times 1. So 4 over 1 is 4. That's a lot of handiwork just to get the answer. Let's do 6 choose 4 and 6 choose 2. Okay. So again, I can do N capital CR. That is my combination here instead of NPR. What did I say? It was 6 choose 4. NCR 6 choose 2. Any of the ones I have, again, I can use right there. If I have my TI calculator and you want to do it that way, it's going to be really similar to the last way we did it. I showed you the permutation. It's the same steps. So it'll be again, first number, math, arrow over to PRB, arrow down to NCR, enter, second number, enter. So combinations, permutations are all in that math PRB section. Stands for probability. So that is where you can get those, or just use Desmos like I showed you. How many different simple random samples of size 4 can be obtained from a population whose size is 20? So sample sizes, grouping, it does not matter order here. So we are going to use a combination. So I'm going to do 20 choose 4. And I will go right to my Desmos. NCR 20 comma 4 inside of parentheses. And I have 4,845 groups of 4 that can be made from 20. And the slides will show you here all the handwork. If you wanted to do it that way, please use the technology. I think that it's better that way. Next up here is what happens if we want to do a permutation, and we can only do this with permutations here, with non-distinct items. What this means now is I want to find the number of ways I can arrange things, but I have some duplicates. So a good example here is DNA. Your DNA sequence has only 4 letters to choose from here. The 4 possible letters are A, C, G, and T, each representing the values, adenine, cytosine, guanine, and thymine. And I apologize if any of you are science people and I butchered those. I apologize. How many distinguishable sequences can be formed using 2 A's, 2 C's, 3 G's, and 1 T? Problem here is this is not just a matter of I want 1, 2, 3, 4, 5, 6, 7, 8 letters. I only have 4 letters to choose from. So what we do is we want to think about this as we know we're going to have 8 positions to fill. I've got 8 positions that have to be filled in with letters. But there's a few different things that happen here. I need to determine how many places to put A in, how many places to put C, how many places I could put G, or how many places I could put T. Working that out here, I have working with A's first, working in order. I have 8 spaces and I need to put A in 2 of them. Once I've done that, I then have 6 spaces left to put 2 C's. Then I have 4 spaces left to put my 3 G's and 1 space for my final T. What they're going to do here is they're going to show you how this formula comes to be. And what ends up happening in this strand here is I end up getting 8 factorial over 2 factorial, 2 factorial, 3 factorial, 1 factorial, z factorial, 0 factorial. There's a formula on the next slide that's going to happen. We have permutations with non-distinct items. However many total you have is on top in your numerator. Okay, so back here, I had 8 positions to fill, 8 factorial. And down here is how many of each piece you have. So I had 2 A's, 2 C's, 3 G's, 1 T, and the 0 is really null and void. I don't need the 0 there. Instead of worrying about this whole part out here, how they did it, we can jump to this spot down here. Now, this part, we have to be very careful in how we enter it into our calculator. Because a calculator is only as smart as the person entering it in. So if you do not enter this into a calculator correctly, it will not give you the correct answer. One way in which you do this, 8 factorial divided by parentheses, and I'm going to put all those other 2 factorial times 2 factorial times 3 factorial times 1 factorial. So option 1 is in parentheses like that. Let's do this way. 8 factorial divided by 2 factorial. Get my answer. And divide that by 2 factorial. Take that answer, divided by 3 factorial, and I get my answer of 1,680. So I like doing it this way because it works a little bit faster. I can put them all on the bottom. If you're working with a TI 83 or 84, you're going to want to, like I said, you can either use parentheses or you'll have to do them separately here. But Desmos is set up to automatically make it into a fraction, so it's easier to do it this way versus doing it in multiple steps. We'll do another example here. How many different vertical arrangements are there of 10 flags? So 10 total flags, knowing we have 5 white, 3 blue, and 2 red. We have non-distinct items, 10 total. 5 are white, 3 are blue, 2 are red. We start with 10 factorial on top, and then the number of whites, blues, and reds in their factorials. And we will get our answer. Again, I will show in Desmos just to show these are a little more complex as we write them. I want to make sure you guys see them. So 10 factorial divided by, and I will open and prepare a parentheses, 5 factorial times 3 factorial times 2 factorial should be 2,520. And that is the answer we got. Recap here. Combination is a selection of objects where order does not matter. We're going to use NCR. Permutation with distinct items with replacement. This was like the letters in the airport, 26, 26, 26. That's more, I always think of that more as a sequence of choices question, so I don't usually think about that one as much, but our book does. So permutation of distinct items without replacing, NPR. I cannot reuse something once I've used it. If they're non-distinct, we have to divide by how many of each kind there are. And in the next section, we are going to literally see all of it together. Addition, multiplication, multiplication with choices, combinations, permutations. You're going to have to read them and figure out what formula it is that we're going to be using. But before we can do that, we are going to go one step further and put some probabilities with these permutation and combinations. In the Illinois lottery, an urn contains balls numbered 1 to 52. From this urn, 6 balls are randomly chosen without replacement. For a $1 bet, a player gets to choose 2 sets of 6 numbers. To win, all 6 numbers must match those chosen from the urn, but the order in which the balls are picked does not matter. Okay, so it doesn't matter that what order they've come in, you just have to have all 6 of them. If order does not matter, we are going to be using a combination. So we need to figure out how many ways we can pick 6 numbers from 52. 52 numbers, 6 are chosen. So we will do 52 combination 6. There are 20,358,520 groups of 6 from 52. Now, when you purchase a ticket, you get to pick 2 groups of 6. 2 out of 20 million. 2 out of 20 million gives you a probability of 0.0000000098, aka far near impossible to win the lottery. It is not likely to win the lottery here. All right, here's what this means. There is about a 1 in 10 million chance of winning the lottery. So you would either have to play the lottery 10 million times to win one time. But again, it's probability. It doesn't always necessarily work like that. You could play 10 million times and never win. It is just how that works. But this is why you don't see people win big lottery values that frequently. A shipment of 120 fasteners that contains 4 defective fasteners was sent to a manufacturing plant. The plant's quality control manager randomly selects and inspects 5 of them. What is the probability that exactly one of the inspected fasteners is defective? Things we gotta do. The number of ways of choosing one defective fastener from 4 is 4 choose 1. It's really 4. There's only 4 ways to choose a defective fastener. I either choose the first one, the second one, the third one, or 4th one. The number of ways I can choose 4 non-defective fasteners is there are 116 remaining, of which I want to choose 4. So I'm doing 2 things here. The first is I need to pick 1 defective from the 4. And then I need to pick 4 good from the remaining 116. What's the probability of getting exactly 1 defective? So 1, if I get 1 defective, I also have to have 4 good. There are 4 total defectives, 116 total goods. So that's where 4 choose 1 and 116 choose 4 come from. The number of ways this can happen is 28,640,980. All right. That is our numerator. That is what we wanted. I wanted 1 defective and multiplies 4 goods. Number of ways that happens is this. So probability takes the number of ways that this happens and divides by the total. So we don't have the total yet. Well, the total comes from our 120 total fasteners, of which I'm choosing 5. That value here is 190,578. 190,578,024. So what we're going to do is put those 2 values over each other. 28 million value over the 190 million value and 0.15. So out of my 120 fasteners that I have, if I pick out 5 randomly, I have a 15% chance that one of them is defective of my 5, exactly 1. The probability of randomly selecting exactly 1 defective fastener is 0.153. So if we selected 5 fasteners 100 different times, we'd expect about 15 of them to have exactly 1 defective fastener. I promise we are going to work on all of these again here in the next section, combining them all together. Just determining, hey, which method am I going to use? And kind of putting it all together. All right. So that is the end of 5.5. And we will see you in the next section.